Hi again, everybody. In the first half of our Chapter 7 video, we talked about alkenes and where they come from, and we talked about how to calculate degrees of unsaturation and how to name alkenes. So if you want some practice with that, go back and watch the Part 1 video for this chapter. This video is going to focus on the second half of Chapter 7 in the McMurry Organic Chemistry textbook, available on OpenStax. Looking first at the stability of alkenes. So if you remember from our previous discussion, alkenes are different to alkanes in that where we have that double bond, we have a point of rigidity. And so we have two isomers now. These aren't conformations like we would have called them for alkanes because we don't have free rotation around that central bond. So these isomers, the cis isomer, where the two groups go on the same side. We talked about cis-trans naming and we talked about EZ naming. So this would be the cis or the Z isomer. This would be trans or E. Remember, cis-trans you can use only when you have two non-hydrogen substituents, one on either alkene carbon. Z and E, the EZ naming system, you can use all the time, but it's required when you have three or more substituents. So the stability here, I hope it makes sense based on what we talked about for conformations of alkanes, that the cis isomer is less stable than the trans isomer. And if you sort of think about this, if we were to view a Newman projection looking at this molecule end on, this is essentially the eclipsed formation where we'd have the two methyl groups eclipsing each other. So we don't normally draw Newman projections for alkenes, but if we were to think about doing that, we would end up with our front and our back methyl groups eclipsing each other. And then likewise, our front and back hydrogens would eclipse each other. It looks something like that, dot in the middle, right? So this is a bad scenario, right? Worst scenario. This one, if we were to look at the trans isomers in Newman projection, it's still eclipsed, right? There's nothing we can do about that because these are sp2 hybridized, and so this whole thing is flat, but at least we've moved the two methyl groups away from each other. And so now we'd have these methyl hydrogen eclipsing interactions instead of this methyl-methyl eclipsing interaction. So don't stress about the numbers throughout this chapter and really through the rest of the book. These aren't numbers you could calculate exactly. This is just saying that given the opportunity to separate using an acid here to break the double bond and then allow it to reform, we would get more of the product forming in the trans configuration than the cis because of energy. And so what we can talk about here is how we could look at that. We can calculate the energy by hydrogenating these. So alkanes can be hydrogenated to give alkanes. This is one of the reactions that we're going to see in the next chapter. But essentially what we do when we do this is that we react with hydrogen gas and a metal catalyst, typically platinum or palladium, and we end up adding a hydrogen to each of these two carbons. We're using the electrons in the double bond as a nucleophile, and we'll end up adding these hydrogens. We can measure the energy released when we do that, when we essentially release this point of rigidity and allow it to freely rotate in the case of butane. If we do that starting with the trans isomer, we release 116 kilojoules for every mole. When we do it with the cis isomer, we release 120. And so we can sort of see here that the cis isomer is 4 kilojoules per mole higher in energy. And that's sort of quantitative data to back up what we know qualitatively. That instability, of course, gets more severe the more bulky this thing is going to be. So a monosubstituted alkene would be the best, and of course cis and trans wouldn't matter here because the interactions are exactly the same, right? If I flip-flop to this carbon so that I was like that, it'd be exactly the same interactions. And that's why we don't really have a cis and a trans isomer when we only have one substituent, or even two substituents on the same carbon. Notice if we were to disconnect this double bond, flip one of these carbons around and reconnect it, we'd have exactly the same interactions. So the same is true when we talk about a trans disubstituted. It's very similar to the 1,1 disubstituted version in that it's sort of the lowest energy we can get, right? But if we now start to talk about the cis version of this guy, or a tri-substituted or tetra-substituted, the energy level is getting higher and higher as we have more and more of these bulky interactions. And of course, it does depend on the nature of the substituents, right? All of these have the same torsional strain. The electrons in these bonds that are physically shown here are exactly the same. It just depends on the substituents. And the bulkier the R groups are, the more pronounced the energy differences would be. So when we go back here and we see having a little methyl group in each position, that gets us 116 versus 120 kilojoules per mole. If these were ethyl groups or isopropyl groups, or maybe full aromatic rings, gigantic structures, then the difference between these two structures would be much more pronounced. So the other major topic in Chapter 7 is electrophilic addition reactions. Now, in this case, we're going to actually study the reactions themselves in Chapter 8, and there are a whole bunch of reactions in Chapter 8. Basically, in Chapter 8, we're going to look at what we can do to an alkene to form a whole bunch of other functional groups. But the first collection of these reactions in Chapter 8 are electrophilic addition reactions, and they all follow the same mechanism. And that's what we're going to talk about now, is the mechanism. Remember from our previous discussions that pi bond electrons are nucleophilic. And so when we talk about an alkene reacting with something, that pi bond can serve as a nucleophile to attack some electrophilic thing and cause an addition to occur. So we saw an example of this actually in Chapter 6 when we first talked about nucleophilic behavior, but we're going to examine this particular reaction a little bit more. So here is 2-methylpropene. When we react it with a binary material, so HCl here, and this in general terms we could say is HX. X here is being used as a placeholder for a halogen. When we have an alkene reacting with a halogen, we're going to end up forming an alkyl halide. I want to point out a couple of things here just before we get going. Oftentimes you'll see a solvent listed by the arrow here. Oftentimes the particular specific solvent that's listed is not essential. In this case, we're doing this in ether because we can sort of put both of these materials in ether and it's not a problem. You could use other solvents here as well. Okay. Down below, this is a little bit of a different scenario, and I just want to point this out to you. Notice that here I'm using an HX acid. So hydrochloric acid is an easy one to get my hands on, and I can just, put in hydrochloric acid. Hydroiodic acid, or hydrobromic acid, or hydrofluoric acid, those are a little bit harder to deal with in their acid form. And so what we're doing here is a really common way to generate in the reaction, what we'd say in situ, generate that acid. And so I'm using a salt. This one happens to be potassium, okay, but I'm using a salt to provide the I- part, and I'm using a strong acid here, in this case phosphoric acid, to generate the H+ part. So by mixing those two together, I'm sort of creating HI on the spot. So rather than adding in HI directly, I'm adding in an iodide salt and a strong acid. In either case, what we are doing here, just like we saw in the previous chapter, is that we are, let me elaborate this a little bit, okay? What we're doing here is we are using those nucleophilic pi bond electrons to bond to hydrogen and create this intermediate, okay? CH3, CH3. Now that guy's got our new hydrogen on it. Okay, so I'm putting the hydrogen on that right carbon there to make the CH2 a CH3. And I will have generated a chloride ion. And then that chloride ion in a nucleophilic attack can bond to form this new bond right here. And so we get this product, 94% reaction. Okay, again, you can't calculate that number on your own, so don't worry about it. But it's a pretty solid reaction. Down here, when I use a different alkene, okay, we see this, the same kind of idea. The first step is going to be protonation to generate the carbocation, like that. And then nucleophilic attack of the halogen on that carbon, okay, to generate our product. So two-step mechanism. First, reaction with H to form the carbocation intermediate. Second, the nucleophilic attack of that displaced halogen ion to form the alkyl halide. We can also do this with water. Okay, so water, if we think about it, is kind of like a binary reagent. So sort of in the way that HX reacted, we can sort of think about water reacting in the same kind of way. However, it turns out if we just use water, because this material, water, is not a particularly good acid, generally speaking, we add in a catalyst, a strong acid of some kind, to, again, be an H donor. All right, so same kind of deal. All right, we'll get our step 1 nucleophilic attack to generate our carbocation intermediate plus on that carbon there. And here I'm just going to show you the hydrogen that got added. Okay, remember there was another hydrogen there too. There is still a second hydrogen here, but I'm showing you the one that got added. And then the oxygen of water can serve as our nucleophile to attack that branched carbon and form this new bond. Okay. Now you're going to say, wait a second, where'd that other hydrogen go? Well, it got lost. This is what I like to call a phantom proton in organic chemistry. Okay, so notice here this acid is being used as a catalyst. Catalysts, remember, are not consumed in the course of a reaction. So what would have originally been an OH2 when water added can easily lose that second hydrogen back to solution to regenerate this H+, and we're left with an alcohol. Okay. So if you really looked carefully at these reactions, you might have said, well, wait a second, Stamper, why did the chlorine add there? Why didn't the hydrogen add there and the chlorine add out here at the end? Likewise down here, I didn't say anything about it, but I added the hydrogen to the end carbon, and then I let the iodide attack carbon 2. Well, why not the other way around? Why didn't I get hydrogen adding to carbon 2 and the iodine adding on the end? Or here, I just put the hydrogen on carbon 2, allowing water to attack carbon 1. Well, why not the other way around? Why didn't water attack down here and hydrogen up here? This is a concept called regiospecificity. And so basically the idea is when we add that hydrogen, okay, when the nucleophilic double bond reaches out to that hydrogen and we have to choose to attach it. Remember, these electrons are shared between the two carbons. So either the hydrogen attaches on the end, which would give us the plus on the middle carbon, and then when the chlorine adds, we would get this product shown on the left side of the product area. Or we could imagine the hydrogen adding to that central carbon, leaving a carbocation on the end, and then chlorine could attack there, right? That does not form. Well, why not? The why not comes from that intermediate, okay? And I'll show you some examples in a minute, but the guy that we have to thank for this explanation is a character called Vladimir Markovnikov. So this guy, born in the heyday of Russian chemistry, earned his degree in 1860, studied in some really famous labs, including with a guy whose name you've probably heard in terms of labware, Erlenmeyer. Got his PhD in 1869. Now, this is around the time, and also in Russia, that that Mendeleev was working out the periodic table. A lot of good chemistry was going on in Russia at the time. Markovnikov got his PhD in 1869 and published this 26-page paper with a 4-page addendum. You can imagine what a 26-page paper, especially one written in Russian, what kind of recognition that would have gotten. It's hard to read, it's dense, whatever. And then this rule that he elaborated was in an addendum to that. So it actually got fairly little recognition at the time, but it turns out it's extraordinarily important. And it's become known now as Markovnikov's rule. And you'll hear this a lot in organic chemistry. Basically, it explains why we get this left product and not the right product. And so what it says here, in my view, is that in the addition of a binary reagent to an alkene, the H attaches to the carbon with fewer alkyl substituents. Or put another way, the H attaches to the carbon that already has more H's on it. And the X attaches to the other carbon. Now why? Okay, that's great. That's a great rule. That's level 1, Markovnikov's rule, and it'll get you there. You'll get the right products, but you won't necessarily get the right mechanism. And why is that? Well, if we think about it another way, if we attach the hydrogen to the carbon with more hydrogens on it already, we will generate a carbocation on that other carbon as compared to this. The more substituted carbocation is the more stable one. And so this intermediate right here is a more stable intermediate than would be if we formed it the other way around. In this particular case, when we have the difference between a primary carbocation and a tertiary carbocation, we've got primary is less stable than secondary, which is less stable than tertiary. So being able to choose essentially between a very stable tertiary and a very unstable primary, there's no question here. We see the primary one just doesn't happen. That reaction pathway does not happen. Now, if we were negotiating between a primary and a secondary as our two possibilities, or a secondary and a tertiary, you might find where both products do form, but the major product will be the one that forms from the more stable carbocation. So let's look at some examples here. Here's 2-methylpropene. And again, if I put the hydrogen on the end and put the positive charge in the middle, I form a tertiary carbocation that's much more stable. Resolution of that intermediate, so chlorine adding there, gives me my sole product. The other way around, I would have put the hydrogen on carbon 2, and I would have ended up with a primary carbocation, which is not stable. I can draw a chlorine attaching there, but this intermediate doesn't form. And so this product doesn't form. I get a sole product up here. If I look at another example, and this is the one we saw when we talked about the ring-shaped, the cycloalkene kind of a setup. Again, if I attach the hydrogen to the bottom carbon, the way it's drawn here, like this, I form a tertiary carbocation on that branch point. That's very stable. And then I can resolve it like this. If, on the other hand, I were to attach the hydrogen at that top carbon of the alkene, I would form a secondary carbocation. That's less stable. And although I can draw the resolution like that, this is not formed, or formed in very, very low amounts. Okay, so that doesn't form because that doesn't form, because the secondary carbocation is less stable than the tertiary carbocation. And so we get problems like this. What product would you expect from this reaction? Now, it probably occurs to you that Markovnikov's rule only applies if we have an asymmetric alkene, right? If I had a symmetrical alkene, it wouldn't make any difference. So if I was talking about, a butene like this, both of these have exactly the same setup. So either way I do this, I'm going to form the same carbocation, whether it's there or there. It doesn't make any difference. So only when I have an asymmetric alkene like this. What product would I expect from it? Well, I'm going to essentially have two options. Either I'm going to attach my hydrogen up here and form a secondary carbocation down there, or I'll attach my hydrogen down here and this carbon would be a tertiary carbocation. I think by now we understand tertiary carbocation will be more stable, and so I would indeed expect my hydrogen to attach here, my chlorine to end up attaching there when I use up that double bond. Okay, and so I can see it looking like that. They didn't show me down here. Remember, we have this bad habit of hiding hydrogens, but the hydrogen that we added there would be the one that would be attached here. There was already one hydrogen attached there. That's still there, okay, but we added a second one. Here's a retrosynthetic kind of an approach. So going backwards, what alkene could you start with to prepare the following alkyl halide? Now, what you want to think about with this kind of problem is, okay, I know I added HX, right? X here must be chlorine. So if I added the chlorine here, right, on this carbon, then that carbon had to be part of a double bond. That double bond could have gone to the left, it could have gone to the right, or it could have gone down, right? And so there are three possibilities here that you could have had. Now, for space's sake, I flipped this molecule over, so don't be confused by the methyl going up. But I can have my alkene going to the left, so here's the carbon I dotted up above, right, that branching carbon. The alkene could have been that carbon to the left, that carbon to the right, or that carbon out to the methyl, the short branch. All three of those would have done the same thing, because in all three cases, I would have added a hydrogen to the less substituted and made the carbocation on the more substituted. Right? They all would have had exactly the same intermediate, and all three of those intermediates, when chlorine attaches, would give me the same product. Okay, so this has to do with carbocation stability. Now, we know that alkyl groups are not particularly electron dense, right? It's not like we could draw any resonance structures to stabilize anything. All we're dealing with here is induction. So if I've got all hydrogens, that would be a methyl carbocation. Hydrogen's got no extra electrons at all, right? Just the bonding electrons, just the 1s orbital. So nothing going on, no stability at all. If I have a primary carbocation, I at least have whatever electrons are in all these bonds, right? This is at least a CH3 group, right? It could be bigger, but all the electrons in here can kind of be polarized, pulled a little bit to offset this carbon positive, right? It's not dramatic, it's not resonance, but a little bit of inductive effect to help out. Of course, if I have a secondary, I've got two groups that can help out, and tertiary is more stable because I have three groups that can help stabilize that central carbocation. All right, the bigger the groups are, the more electron rich they are, the better. Of course, if I have resonance available to me, that's even better. But by inductive effect, this is why alkyl groups help. All right, so what's the proof? Okay, where's the proof that this is right? Well, we don't know for certain, but the evidence is pretty strong. All right, so here is 3-methyl-1-butene. We see here we have the alkene. We have a methyl group on position 3 over there. And when we react it with HCl, we get the product that we would expect, right? Shown here on the left. And that is where we've attached hydrogen to the end carbon, right here in pink. That would have generated a secondary carbocation. That's the best we could have gotten here. And then chlorine could have attacked there, right? So we get what we expected. However, we get another product as well. And this product is a little bit weird. This product shows hydrogen attached to carbon 1, or what was carbon 1 in the alkene, but the chlorine not attached to carbon 2, in fact attached to carbon 3. And if we track these atoms, if we label this, maybe we introduce a deuterium here at this position, so this hydrogen can be measured, we see this blue hydrogen moving from carbon 3 over to carbon 2. Those numbers are of the original alkene, right? So what? Why? What happened? Well, this has to do with that carbocation stability stuff. So here's our normal carbocation mechanism. Here's what we would have expected, right? Nucleophilic attack of the pi bond on this hydrogen, displacing a chloride ion. So there's your chloride ion right there with its little electrons it got from its bond. That's our secondary carbocation. That's what you would have predicted. And then we would have resolved that, the nucleophilic attack on that carbon to give us our product, right? Makes sense. How do we get the other one? Well, the way that we got the other one is because this carbocation is secondary, but it's got a branched carbon next to it. If only this carbon was our carbocation, that'd be a tertiary carbocation. That'd be so much more stable. Well, we can do that if we imagine this hydrogen migrating next door. Okay, I'll show it to you on the next slide. If we imagine that blue hydrogen migrating one position over, taking its electrons and moving one position over, this is called a hydride shift. H-, remember, is called hydride. So what we're doing is we're moving the electrons and the H next door. And by doing so, we get the more stable tertiary carbocation right there. So we're trading up. We're going from a secondary carbocation that was okay to a tertiary carbocation that's much more stable. And after we've done that, then we can get our resolution like we normally would for a carbocation, but now our chlorine is over on what had been called carbon 3. Now we have to reevaluate the naming. That would be carbon 2 of this resulting chloroalkane. Okay, so don't get tripped up on the numbering. The original numbering with the alkene started on the right because the alkene was over here. But now when we name this product, we have to look at it fresh. Okay, it doesn't matter what the numbers were before. We would number from the left. 1, 2 methyl, 2 chloro. Okay, and then we go on. So we get both of these. This one came from a tertiary carbocation, this one from a secondary. Normally the tertiary would be way more popular, right? More stable, much higher percentage, but it required this extra step. And so they told us in the book that this is actually about a 50-50 split. Hydride shifts are very, very common. So what I want you to do when you're doing these problems, okay, when you're doing problems like this, what's the major product or what products are formed when we do this thing? Draw the carbocation intermediate first, okay? So you got to promise me that. You're going to draw the carbocation intermediate because when you see this, look at it. If it's already a tertiary carbocation, fine. Just add the nucleophilic, in this case chlorine. if it's a primary or a secondary, look next door and see if doing a little hydride shift like that would make it better. We wouldn't shift this hydride from the right, okay, because that would give us a primary carbocation. That'd be worse. But if we shift this hydride, that gives us a tertiary carbocation right there, and it's better. So always draw the carbocation first. If it's not already as stable as it can get, look next door and see if you can get more stable. We're going to be able to get more stable by doing a hydride shift if there's a hydrogen on that neighboring carbon. Or another way we can look at it, you see the blue giving away the punchline, but if we were to do a reaction like this with this 3,3-dimethyl-1-butene, okay, again, nucleophilic attack of the pi bond on hydrogen gives us our protonated end bit here, gives us a secondary carbocation. We can resolve that like normal, right? So chlorine attacks like that, or chloride ion rather, attacks like that. We get our product we expect, right? No big deal. However, notice here, we don't have a hydrogen next door. We do have a methyl, and these guys can move too. This is what we call a methyl shift. So again, I've generated my initial carbocation. I'm happy with this. I look at that carbocation and I say, okay, that's a secondary. I can't shift anything from the right carbon because that would give me a primary carbocation left over. That's no good. This one could be tertiary if I shift this methyl group. And so instead of the normal resolution here, if I shift that methyl group over, okay, the blue methyl moves over here. That gives me my tertiary carbocation right there that then can undergo our normal nucleophilic resolution like that to give me another product. The only two things you're going to shift are a methyl group with its electrons or a hydride with its electrons. That's it, methyl and hydrogen. As the groups get bigger than that, they're too bulky, and steric considerations block this kind of movement. But hydrides can do it, and methyls can do it. So what you want to do is, again, draw out your carbocation intermediate that you expect. If that initial carbocation is not already tertiary, look next door, both directions. Look next door and see if you can find either a hydrogen or a methyl that if you shifted it, it would give you a more stable tertiary carbocation. And that one typically is going to be a significant product. All right, and so there's two considerations here. We talk about stability and we talk about rate, okay? We saw some energy diagrams in the last chapter, and we talked about the difference between the energy levels here, which would have something to do with delta G and our equilibrium position, our capital K value. And then we talked about the difference between transition state energies. The higher the activation energy is, okay, so transition state 1, the higher the transition state energy is, the slower that reaction is going to be. So what's shown here in pink is the slower reaction leading to a less stable intermediate. All right, and then we'd have another bump that would do the resolution part of this reaction. The green one is the faster reaction leading to a more stable intermediate. Okay, these paths never cross. So you will never have a fast reaction leading to something unstable or a slow reaction leading to something stable. Okay, they don't cross like that. But remember that from the last chapter, the difference in energy at the end or in the intermediate step, that difference has to do with total energy. So delta G and KEQ, the transition state energy in the middle there, that's related to rate. And so why are we talking about this intermediate thing? Well, there is another chemist by the last name of Hammond, whose postulate here talks about that transition state. Now, I told you before that we can't isolate transition states. We can't purify them and study them by crystallography or something. So Hammond's postulate is I guess you could say theoretical, but talking about how the structure of the transition state is going to resemble the structure of the nearest stable species. What does that mean? Well, in the left diagram, we're showing a large activation energy, okay, to get up to a transition state, and then the product is relatively high in energy compared to the reactant. The transition state here would be said to resemble the product most closely. They're closest in energy. So the difference here essentially is smaller than the distance here. So remember we talked before about transition states and how it's this intermediate, right? Bonds are in the process of breaking and new bonds are in the process of forming. The transition state here would look a lot more like the like the product, closer in energy than the reactant. However, a different reaction described by the diagram on the right, we can see the transition state here very close in energy to the reactant. Hammond's postulate would say that the transition state of this reaction mimics the reactant very closely. And then once it releases all this energy to get down to the product state, that looks very different. So Hammond's postulate you can sort of think about as being, I want to say theoretical, but being something that's logical, that you can conclude based on these energy diagrams. All right, and so between the two discussions that we've had and this set of slides, we've got a few major take-home messages. So you need to understand degrees of unsaturation from the beginning, as well as alkene nomenclature. So using the cis and trans system, if you'd like, the E and Z system, talking about alkene stability, so being able to rank alkenes based on the orientation and the size and makeup of their substituent groups. You won't be able to necessarily predict exact energy values, but you can rank the relative stability of different groups, different molecules. Thirdly, we've got Markovnikov's rule. So what does it mean to have a stable carbocation? That concept of tertiary being more stable than secondary, more stable than primary. And so we can predict what product will form from Markovnikov's rule. And then this concept of hydride or methyl shifts that can be responsible for rearranging that carbocation intermediate. Again, that only happens if you start with something that's not already a tertiary carbocation, and then you have a hydride or a methyl next door that you could move to make it more stable. And finally, a qualitative understanding of Hammond's postulate. Using an energy diagram, you could identify whether the transition state looks more reactant-like or more product-like. All right, looking forward to the next chapter, we're going to be looking at alkene reactions, and we're going to use Markovnikov's rule quite a lot. What we're going to see is that we now have a set of tools for reacting alkenes where many of them react in the predicted Markovnikov's way, and so we get products that follow Markovnikov's rule. We also have tools for doing certain reactions where we can reverse that regiospecificity. And we can do an anti-Markovnikov addition by using different reactant conditions, different catalysts, whatever it might be. So we'll see both of those. So until that time, when we go through those, finish up chapter 7. If you have questions, of course, email me, and otherwise, have a really fantastic day. Take care.